Welcome back, deep divers. You know those choose-your-own-adventure books? This deep dive is kind of like that. Instead of like a spooky mansion, we're poking around the architecture of early AI attention models.
Yeah, exactly. And just like those adventures, there are some paths not taken that are super fascinating to revisit.
So true. You sent over this paper from Google DeepMind back in 2014, and the title's a mouthful. Something about recurrent models of visual attention.
Yeah.
Sound pretty intimidating. What's the TLDR for a busy, techie on the go?
Basically, they were trying to teach a machine to see like we do, not all at once, but by focusing on the important parts, kind of like how you'd skim a web page.
Right.
You're not reading every single word.
Okay, so before AI could translate languages, they were wrestling with this problem of making machines process entire images at once.
Right, it was a huge bottleneck computationally. Like, imagine trying to understand a photo by analyzing every single pixel.
Yeah.
It's slow, inefficient.
It'd take forever.
This paper tackled that head on.
Okay.
Their solution. Digital side-eye.
Digital side-eye. Now, there's a term I haven't heard before.
They called it the glimpse. So instead of analyzing every single pixel, the model takes a series of glimpses, small focused looks at specific parts of the image.
Kind of like how we scan a page or look around a room, just focusing on the interesting bits.
Exactly.
Clever.
Yeah.
But how does the model know where to glimpse? It can't be random, right?
You're right, not random at all. This is where it gets really cool.
Okay.
They use something called a recurrent neural network, or RNN. Think of it like short-term memory for the AI.
Yep.
Each glimpse informs the next one.
It's constantly learning as it goes, refining its strategy with each glimpse.
Exactly. The model takes a glimpse, the RNN processes what it sees, updates its internal state, and then that state influences where the next glimpse will be.
So it's like building on its knowledge, right?
Exactly. It's like a detective piecing together clues from each glimpse.
I can see how that would be way more efficient than just trying to process everything at once. But how do they actually test this? Did it actually work?
So they started with a classic test for image recognition models, MNIST. It's a database of handwritten digits. You've probably encountered these in CAPTCHAs.
Oh, yeah.
Those little puzzles where you have to identify blurry numbers.
Ah, yes. Those squiggles that make you question your own humanity. So they showed these digits to the model. Did it pass the test?
It did. They started with the digits nicely centered,
Okay.
kind of like a home court advantage. And what's interesting is that each extra glimpse the model was allowed to take actually improved its accuracy.
That makes sense. The more glimpses it gets, the better it can see the digit, even if it's a bit blurry or messy.
Exactly. But of course, they didn't stop there. They wanted to see how it handled more challenging situations.
So what do? Unleash a torrent of blurry images at it?
In a way,
Yeah.
they created what they called cluttered translated MNIST.
Okay.
Imagine a handwritten digit, but it's surrounded by fragments of other digits, like someone spilled a box of number magnets, you know?
Oh, no, they unleashed the digital clutter.
It's designed to be tricky even for humans.
Everyone's nightmare. That sounds ridiculously hard.
Yeah.
Was the model up to the task?
This is where it gets really interesting.
Okay.
The attention model, with its selective glimpses, was actually better at handling the clutter than a traditional convolutional network.
Wait, seriously, you're telling me that by focusing on just a few key areas, this glimpse model could outperform models that were trying to analyze the whole image?
That's right. It highlights one of the core advantages of attention mechanisms,
Okay.
their ability to hone in on the most important information and filter out the noise. But identifying digits is one thing. They
Right.
wanted to know if this model could handle something more dynamic.
Okay, so it can find a digit in a crowded room, but can it play games?
They tested it on a simple game called Catch. Picture a single pixel falling from the top of the screen, and the model has to control a paddle at the bottom to catch it.
A single pixel. Talk about a needle in a haystack. How could it even see that, let alone react in time? Did it actually learn to play? It did. And get this, they never explicitly programmed it to track the ball. It learned that on its own, purely by focusing its glimpses.
It's a bit like watching a baby learn to track objects with their eyes, figuring out that focusing attention is key to understanding movement.
That's both amazing and a little spooky. But this all sounds pretty high level. How did they actually build this glimpse mechanism? Was there some secret sauce?
Well, like any good magic trick, it comes down to how the illusion is constructed. They had to create a digital version of how our eyes work, but with the ability to focus on specific areas. They called this the retina of the model.
Okay, so the retina is like the model's eye, but instead of capturing the entire scene, it's focusing on a small area.
Exactly. It's like looking through a high-powered camera lens. You get a super detailed view of a small region while everything else is blurred out.
So it's getting a concentrated dose of information from that specific spot. That makes sense, but it still needs to process that information and decide what to do next.
Right. That's where the glimpse network comes in. Think of it as the brain behind the retina, analyzing what it sees and figuring out where to look next.
So it's analyzing the focused information from the retina and making decisions based on that, like a detective using a magnifying glass, looking for clues.
Precisely. And just like a detective might use different magnifying glasses to get a better look at different types of clues, they designed the retina to have multiple scales, allowing the model to adjust its focus, zooming in on details, or pulling back for a wider view, all within that focused glimpse.
That's smart. So it's not just where it looks, but how it looks. This is getting really interesting. Can we actually see an example of this glimpse in action?
Absolutely. Take a look at figure 3 from the paper on your screen.
Wow, it's like watching the AI, I think. You can see the path that glimpse takes as it scans the image.
And notice how it doesn't waste time on the empty areas. It goes straight for the digit, even with all that clutter around it.
It's like it knows exactly what to look there. Like it's built up an internal model of what a digit should look like. This is way more sophisticated than I imagined.
And remember, this was still relatively early days for attention models. They were just beginning to explore these ideas.
Speaking of early explorations, the paper mentions that this retina is made up of square patches. What's that all about?
Essentially, instead of feeding the glimpse network a single blurry image of the glimpse region, they divided it up into smaller squares centered around the glimpse location.
Okay, so it's like taking a bunch of snapshots from slightly different angles within that focused area. Why go through all that trouble?
It's all about helping the model pick up on details and patterns at different scales. Think about trying to identify a flower. Looking at the whole flower gives you some information, but examining the individual petals up close gives you a richer understanding of its shape and texture.
So it's not just about seeing the whole picture, it's about seeing the details within the picture.
Exactly. They experimented with different numbers and sizes of these patches, trying to find the sweet spot for different tasks.
Okay, so like Goldilocks, they were searching for the just right combination for the retina. What did they find?
Well, it wasn't about finding a single magic configuration. They discovered that the best retina setup actually depended on the task.
So different tasks, different ways of seeing, makes sense. But can you give me an example? What worked for the digits versus that catch game?
For the Mnih digits, they found that a small number of larger patches worked well when the digits were centered. You don't need to see every nook and cranny to tell a 7 from a 3, right?
The overall shape is usually enough. But what about with all that clutter they added? Did they need to adjust the retina then?
They did. When they introduced the clutter and started moving the digits around, they found that a larger number of smaller patches worked better.
So more like a detective meticulously combing through a messy crime scene. They needed to zoom in on the details.
Exactly. And for the catch game, they found that having multiple scales was crucial. Remember, the ball is just a single pixel, so the model needs to be able to zoom in for precise tracking, but also zoom out to anticipate where it's going to go next.
It's fascinating how they could adjust this retina based on the task. But there's one thing I'm still wondering about. How does the model know where it's looking? I mean, knowing what you're seeing is important, but don't you also need a sense of location, a bigger picture?
You're absolutely right. And this is where the concept of location encoding comes in. They had to find a way to give the AI a sense of space.
Okay, so it's not enough to just process what's in the glimpse. The model needs to understand where that glimpse is located within the whole image. But how do they actually encode the location? Was it as simple as giving it X and Y coordinates?
In this case, yes, it was that straightforward. They used the X and Y coordinates of the glimpse center, with the top left corner of the image being 0, 0.
So the model always knows where it is in relation to that starting point. But this raises an interesting question. They were working with fairly small images, right? What happens if you scale this up to a huge image? Does that simple system still work?
That's a great question, and it highlights one of the limitations of their approach at the time. As image size grows, the simple coordinate system might not be as effective. It'd be like trying to navigate a whole city using a map of just your neighborhood. You might get lost pretty quickly.
I can see how that would be a problem.
However, keep in mind, this research laid the groundwork for more sophisticated location encoding methods that came later. This was just the first step towards giving AI a sense of place within a larger visual space.
That makes sense. So we've got the retina, the glimpse network, and now location encoding. That feels like a lot of groundwork just to get the AI ready to take a glimpse.
It is, but each component is crucial for this selective attention mechanism to work.
And remember, this paper is called Recurrent Models of Visual Attention, and we haven't even touched on the recurrent part yet.
You're right, we've been building up to that. The recurrent part is where the magic of learning and sequential decision-making happens. This is where we start to see the AI mimicking how our own brains might operate.
Woo, now that sounds interesting. Is this where it starts developing a mind of its own?
Huh. Not quite, but it is where we start to see the model learn from its past glimpses and use that information to guide its future actions.
Okay, now I'm really intrigued. Walk me through it. How does this recurrent part actually work?
At the heart of this model is a recurrent neural network, or RNN. Unlike traditional networks that process information in a single pass, RNNs have a built-in memory.
So they can remember what they've seen before. Like a computer with a memory instead of just the calculator.
Exactly. They have loops within their architecture that allow information to persist over time. In this model, the RNN takes the output from the glimpse network, what the AI saw, and combines it with its memory of previous glimpses.
So it's like taking notes on each glimpse and referring back to those notes before deciding where to look next.
That's a great way to put it. It's this memory and ability to learn from experience that allow the model to develop increasingly complex glimpse strategies.
Okay, so it's not just randomly jumping around the image. It's using its past glimpses to make smarter decisions. But how does it know which strategies are good and which are bad? If there's someone telling it, hey, you should have looked over there.
Yeah, that's where reinforcement learning comes in. Instead of learning from labeled data, the model learns through trial and error, guided by rewards and penalties.
Ah, so it's like training a dog. Give it a treat when it does something good, maybe a little scolding when it messes up. But in this case, the treats are what? Higher accuracy on the digit classification. Successfully catching the falling pixel in that catch game.
Exactly. The rewards are tied directly to its performance. If it takes a series of glimpses that lead to a correct classification, it gets a reward signal. If it misses the falling pixel, it doesn't. Over time, it starts to learn which glimpse patterns lead to higher rewards and better performance.
It's amazing how much this approach mimics the way humans learn. We try things, we see what works, and we adjust our behavior accordingly.
Precisely. And that's what makes this so powerful. It opens up the possibility for AI systems to learn complex tasks without needing massive amounts of labeled data or explicit programming.
This is blowing my mind. But let's bring it back to the paper. How did this whole model actually perform? Was it as revolutionary as it sounds?
The results were incredibly promising, especially for that time.
Give me the highlights.
For the Mnih digits, even with a limited number of glimpses, their attention model achieved accuracy comparable to, and in some cases even surpassing, traditional methods.
Wait, really? So even though it was only looking at a tiny fraction of the image, it could still compete with models analyzing the whole thing?
Absolutely. And remember how we talked about the clutter being a challenge? Well, the attention model actually performed better when they made the task more cluttered.
That's wild. Because it could just ignore all the irrelevant stuff and focus on the important bits.
Exactly. And as for the catch game, well, after being trained on millions of frames, it learned to track the ball and move the paddle to catch it with impressive accuracy.
No way. All without being explicitly programmed to track anything? That's incredible.
It is. This experiment really demonstrated the potential of reinforcement learning and this idea of letting the model discover its own solutions through trial and error.
This research was almost a decade ago, though. I'm dying to know.
Yeah.
How has this field evolved since then?
This paper was truly groundbreaking. It really opened the floodgates for research in attention mechanisms, leading to major breakthroughs in image recognition, natural language processing, and even, as you mentioned earlier, machine translation.
So those seamless translations we use today, they have roots in this glimpse and RNN model we're discussing.
You could say that. This paper helped researchers realize that you can achieve much better results by focusing on the most relevant information, just like our brains do, instead of trying to process everything at once.
That's amazing. And to think, all this came from teaching a computer to play a simple game of catch with a single pixel.
It's incredible, isn't it? Sometimes the simplest ideas lead to the most profound discoveries. But we're just scratching the surface here. There's so much more to this story.
No, unfortunately, we're running out of time for today's deep dive.
Indeed. But before we go, there's one final thought-provoking question the researchers pose in their paper. What if, they asked, instead of trying to build machines that see and think like us, we're actually uncovering fundamental principles about how intelligence itself works?
Wow, it gives me chills. Are they suggesting that by studying AI, we might unlock secrets about our own minds?
It's a fascinating question, isn't it? After all, our brains are still the most complex and mysterious entities we know of.
And to think it all started with a simple idea, teaching a machine to take a glimpse. Where will that glimpse lead us next? That's something to ponder. But for now, we'll have to leave it there.
Indeed. Join us next time as we dive deeper into the world of AI.
Until then, deep divers, keep those minds curious. It really makes you wonder if we're on the verge of some kind of grand unified theory of intelligence, biological and artificial.
It's certainly a tantalizing thought. But even if we don't crack that code right away, the practical implications of this research are already huge.
That's right. For a listener who might be thinking, this is all fascinating, but how does it impact me? What are the key takeaways here?
I think the biggest takeaway is the power of selective attention. In a world flooded with information, knowing how to focus on what's important is crucial for both humans and the machines we build. This paper highlighted that back in 2014, but it's even more relevant today.
So it's not just about processing more data faster, it's about processing the right data at the right time.
Precisely. This research reminds us that efficiency and focus can be just as important as raw computational power.
It's like that old saying, work smarter, not harder. But in this case, it's see smarter, not more.
Absolutely. And another key takeaway is the potential of reinforcement learning. This idea of training machines through trial and error, letting them discover their own solutions, has led to incredible breakthroughs. And we're only just beginning to explore its possibilities.
It's exciting and a little bit daunting at the same time. Who knows what amazing things we'll be able to achieve as we continue to unlock the secrets of AI.
Indeed. And perhaps, just perhaps, we'll learn a thing or two about our own minds along the way.
Now that's a thought-provoking note to end on. Until next time, deep divers keep those glimpses sharp and those minds curious.